All right, I'm going to draw that Venn diagram that we did yesterday. Vertical motion as sort of a subset of particle motion. So yesterday we did vertical motion. Today we'll do particle motion. And so there'll be a lot of overlap. The big difference is that with vertical motion, S of t is always 1/2 at squared plus v0t plus s0. I've written that a whole bunch of times, but that's okay. It gets in your brain the more you use your hand to write it. That's for an object that's only under the influence of gravity. That's why that matches with all the physics stuff, 'cause that's a physics thing. For particle motion, we'll have a different function for position, and that's the big difference between the two. The rest of the derivatives and velocity, acceleration, all that stuff kind of matches up. It's just you have a different starting equation to start the problem with. If s equals f of t is the position function of a particle that is moving in a straight line, so particle motion we normally think of as left and right, or forward and backwards. So it's not up and down, because up and down introduces gravity, and then we're doing vertical motion. So particle motion is normally left and right, or forward backwards. We think of it as like on some surface so that the gravity's not affecting the motion. Particle is moving in a straight line. Then the instantaneous velocity of the particle is the rate of change of the displacement with respect to time. That's a lot of words to say that the velocity is the derivative of position. That's the same thing we had yesterday. So that's one of the things that's the same about it. And the acceleration of the particle is the rate of change of the velocity with respect to time. Again, that's the fancy way to say that acceleration is the derivative of the velocity. So those two things are the same. So the big difference is the starting point, the starting equation. When it's vertical motion and gravity is involved, it's always this. When it's particle motion, we're almost always, I don't want to say always, but I can't think of a time when we don't. We're going to give you this position function. You can see it in that example right there. We'll give you the position function, and then you'll have to basically find velocity, find acceleration, and answer whatever questions go with it. All right, first example. The position of a particle that is moving in a straight line is given by the equation t cubed minus 6t squared plus 9t. T is in seconds, s is in meters. Find the velocity at any time t. Well, velocity is still the derivative of the position. So 3t squared minus 12t plus 9. Tempted to find the acceleration while I'm in the derivative mode, but I guess it'll ask for it later. What is the velocity after 2 seconds? Well, so all I have to do is take the velocity equation and plug in 2. And you could be done and leave it at that if you wanted to. Let's see, that would be 12 minus 24, negative 12, plus 9 is negative 3. After 4 seconds, again, you need to show one of those. You don't have to show both. If you want to just go straight to the calculator, you've told me what you're doing. You're finding v at 4, and you're just going to use the calculator to do so. So you type it into the calculator, and you get 9 meters per second. And that's acceptable for showing your work, because I know that all you did was type it in the calculator. So again, this safe stop, you can show this, or you could show it at this step, but you got to show one of those. You can't just write 9, because I don't know what 9 is, especially when there's 2 questions. When is the particle at rest? What's rest mean?
0.
What's 0?
Velocity.
So velocity is 0. I'm going to factor out the 3 and hope that the rest factors. And it does. And we need to be careful, because sometimes we can get those negative times that pop up, and we just have to throw those out because that doesn't count. But both of those are positive. So at 3 seconds and at 1 second, the velocity is 0. When is the particle moving forward in the positive direction? So I want to know when v is greater than 0. I think what I need here is a number line, and sort of that first derivative test where we set up the intervals. And we'll stop at 0, because I don't care what happens when we're less than 0. So I need to test some intervals, because I know the only zeros are at 1 and 3. So I'll do some test points and see what's going on here. So v of, well, you know what? I could plug in 0, so let's make that one easier. So v of 0 is positive. Oops, make sure we identify label what we're doing with the graph there. So v is positive. V of 2, let's see, that would be 3 times 4 minus 12 times 2 plus 9. That's going to be, we did this already.
Yeah.
A lot of times this happens on AP test, if you're paying attention on multiple part test. It's like, they already asked me for V2 and V4. That seemed like a random thing to ask for until I set up my number line, and it sure would be helpful if we knew what V2 and V4 are, but we do. At 2, V is negative 3, and at 4, V is positive, because we found that already. So that would mean V is greater than 0 from 0 to 1, and from 3 to infinity. Part E. Draw a diagram to represent the motion of the particle. Okay, this would be one of the new things for this unit that we haven't done before. Like all the other stuff so far, that's using stuff we know pretty similar to what we've done. This we've not done before. Another name for this is a motion diagram. So we want to sketch out what this particle is doing. And so to start with, let's plot the points where v equals 0. And plot s of 0. Probably should have done s of 0 first, so we know where to start this thing. So here's a number line, but this number line isn't a number line of time, it's a number line of position, because we want to get like a visual of what is this particle doing. So for this one, when time is 0, our particle's at 0. So we happen to start at 0. It changes directions, or it's at rest at 1 and 3. So I also want to find, we should put this over here, S of 1 and S of 3. Because I know it's positive until I get to 1, so I know it's moving to the right. I just don't know how far until I find S of 1. So that would be 1 minus 6 is negative 5, plus 9 is 4. And then we like to label that. So at t equals 1, we're at s equals 4. And we know it changes directions at 1, so it's going to turn around and head the other direction. But I don't know how far back it goes until I find S of 3. At 3 seconds, I need to figure out, how far back does it go. So I plug in 3 to my S equation. 27 minus 54 plus 27, that's going to be 0. So that's kind of a fluky thing. That doesn't always happen, but it comes back to where it started at t equals 3. And then it turns around and goes positive from there, so I need one more spot out there. I need S of something to kind of verify. I mean, I know it's headed out this way, but I want to get a better idea of that. So let's do S of 4 just to see where we're at. We might be way out there with the 4 cubed there. Four cubed minus 6 times 16 plus 36. Oh, it's 4. T equals 4. Be careful though, it doesn't stop at 4. That was me just checking. Its velocity is positive the rest of the way. So we finished our motion diagram. We've got a picture of what the particle is doing. It moves to the right for 1 second and reaches 4. Then it goes back for 2 seconds and gets back to 0. Then it goes to the right the rest of the way. That's a motion diagram. That's the big new thing for today. And once you draw that correct, it really helps the rest of the problems, or the rest of the questions. Find the displacement. Oh, look at F and G, displacement versus distance. Find the displacement of the particle during the first 5 seconds. So displacement is just where you are relative to where you started, right? It doesn't matter how you got there, right? From physics, you remember this? Remember if you run around the track 4 times, you've run a mile, but your displacement is what? 0. So displacement is just where you are relative to where you started. So S of 5 minus S of 0. Where you are relative to where you started. S of 0 we already found. S of 5 we did not find yet. But I plug it into my formula for S, and I get 20. So in the first 5 seconds, you're 20 meters away from where you started. But total distance, in fact, maybe we should put that on our, do one of those number line break things here. At t equals 5, you're out to 20. Total distance traveled? Well, if you use the motion diagram, then you just kind of add up the pieces. So you don't have to write it out this way, but from 0 to 1, we went 4 meters. From 1 to 3, we traveled 4 meters. Forward and backward doesn't matter, right? Total distance, right? You think about running on the track, it don't matter which way you run. If you're running 400 meters, it's not 400 positive or negative. You've run 400 meters. And then from 3 to 5, that was from 0 to 20. That was 20. So the total amount we ran, or the particle traveled, you don't want to be running, is 28 meters. But again, a good motion diagram really helps with displacement and total distance. Questions on that? The motion diagram is what gets people on the test, I guess, because it's really the only new thing. Everything else is pretty straightforward. H, find the acceleration. So that's the derivative of velocity. So I got to go grab velocity equation, take its derivative, 6t minus 12. That would be the acceleration at time t. The acceleration at 4 seconds. 24 minus 12 is 12. Oh, let's be careful about units here. Acceleration is meters per second squared. Graph the position, velocity, and acceleration functions for 0 to 5. Well, use a calculator for that. So grab a calculator. You can borrow one of mine if you need to. So I'm just going to put them in for y1, y2, y3. I am not going to look at them all at once because I think that would get confusing. Maybe once I look at them one at a time I could do that. But I'm going to turn off the second two and only look at the first one. I only care about 0 to 5. I guess I could go 0 to 6. I don't know about y min and y max yet. I don't know what's a good scale for that. So we'll just leave it as -10 to 10 and see what happens. So this is my position graph first. So it's, I don't know if this is terribly helpful, but it stays positive. It goes out to, this sort of matches our motion graph. When t is 1, we were up at 4. When t is 3, we were back to 0. In fact, our motion graph kind of looks like that, right? We went out, we came back, and then we headed out again. Let's look at velocity. So turn that one off, turn velocity on. I kind of know what it should look like because I did a velocity number line up here. It should be positive, negative, positive. Positive, negative, positive. Okay, so that makes sense. And then lastly, it also makes sense that velocity is a parabola. So we saw a parabola. Acceleration is just a line, so that's going to be the boring graph, but there it is. And you could look at them all at once, but I don't know that that would really be helpful. I think that might be more confusing than helpful. So for a graph, we would just have you use a calculator. When is the particle speeding up and slowing down? This is the other new thing that's kind of tricky. Speeding up and slowing down. All right, speeding up. So the easy way to think about speeding up is if your velocity is positive, let's think about this. Think about driving your car. So you're moving forward, so your velocity is positive. What does your acceleration have to be for you to be speeding up? Positive. But if you're going backwards in your car, so you're in reverse, and you're moving backwards, if your acceleration is positive, that means you're sort of trending in the positive direction. That would mean you're slowing down. If you want to be speeding up in reverse, so you hit the gas, but your acceleration would actually be negative because you're speeding up in the negative direction. So speeding up means that A and V have the same sign. So the positive one's the easy one. You're moving forward, you press the accelerator, you go faster, you're speeding up. The backward one is a little bit weird. So you're in reverse, you're backing out of your driveway, you hit the gas pedal to go faster, you're speeding up because you hit the gas pedal, but your acceleration is negative because you're going faster in the backwards direction. So if A and V have the same sign, if they're both positive or both negative, then you're speeding up. Slowing down is just the opposite, but we can talk through it. If your velocity is positive, so you're driving down the road, you press the brake pedal to slow you down, that's the purpose of the brake pedal, you are decelerating, your acceleration is negative. Now here's the weird one. If your velocity is negative, so you're in reverse, you're backing out of your driveway, you kind of reach the end of the driveway, and you don't want to accelerate into your neighbor across the street's yard, so you press the brake to slow down. That's what slowing down is. Your velocity is still backwards, but your acceleration is positive because you're sort of trending in the positive direction. You're slowing down and you're about to be going forward. So your acceleration is positive even though you're backing up. Is that crazy or okay? Both would be okay. So slowing down means that acceleration and velocity have different signs. So you can think through the driving scenarios every time you hit this problem, or you can just remember if V and A have a matching sign, then I'm speeding up, either forward or I might be speeding up backwards if they're both negative. If they have different signs, right, acceleration is how is the velocity changing? Well, if my velocity is positive but it's changing negative, then those are kind of fighting each other and you're slowing down. Or if your velocity is negative but you're fighting it in the other direction, then you're slowing down. It's hard to think about, but it's not hard to remember that if the signs match, then you're speeding up. If the signs don't match, you're slowing down. So now back to this problem. When is the particle speeding up and slowing down? So I need to think about the signs for A and for V. So I think two number lines sort of overlapping number lines, and I can look and see who's positive where. We kind of already did the velocity number line. It was positive from 0 to 1, it was negative from 1 to 3, and it was positive from 3 on. Acceleration, we didn't do a number line for acceleration, but it wouldn't be hard. At t equals 2, it changes. And let's see, less than 2, we would be negative, and more than 2, we'd be positive. And that may have been why it had us graph that as well. There's the acceleration graph. Less than 2, it's negative. Greater than 2, it's positive. Now, some people can look at the graph like that and figure out what's going on. I kind of overdo it and put pluses everywhere it's plus and minus everywhere it's minus. Because then I think it's easier for me to tell. I mean, maybe this is overkill, but to me that helps me see what's going on. So something's happening at t equals 1, something changes at t equals 2, and then there's another change at t equals 3. So from 0 to 1, are we speeding up or slowing down? Slowing down. They have different signs. From 1 to 2, they're both negative, so we're going backwards and speeding up backwards. So we're speeding up from 1 to 2. From 2 to 3, they have different signs, so we're slowing down. And from 3 on, they're positive, positive, so we're going forward and we're speeding up forward. We're speeding up. So I guess if we want to consolidate all of that, we're slowing from 0 to 1 and 2 to 3. And we're speeding up from 1 to 2 and 3 to infinity. So the number line thing comes back, and then you're looking for where are the signs matching, where are they different. Questions on any of that? All right, I think the back will go quick. But again, anytime you've got a graph, you better be real careful about what graph you're looking at. The figure above shows the velocity. So this is the velocity graph. When does the body reverse directions? Well, it reverses direction when v changes signs. Okay. Sort of the theory behind all this we've done before. We're looking at the graph of a derivative and we're answering all kinds of questions, so we just have to be real careful. V changes signs at t equals, I don't think we can say t equals 0 because we don't really know what was happening left of 0. But t equals 2, t equals 7, and we can't say t equals 10. It doesn't really change directions. It stops, but we don't know what it does next. When is the body moving to the right? Well, that would be when v is greater than 0. So that would be when velocity, which is my graph, is bigger than 0. So that would be 0 to 2, and 7 to 10. It's moving left when v is negative. So when v is below the axis, so that is from 2 to 7. When is the body moving at a constant speed? So what times is the velocity constant? From what to what? 3 to 6. And be careful, it doesn't mean the particle is constant. It's still moving, but it's moving with a constant speed. When is the body's acceleration? Well, acceleration is dv dt. So that's the slope of v. So the slope of the velocity. And we have a picture of the velocity. So the slope of the velocity is positive from 0 to 1 and from 6 to 8. The slope of the velocity, the slope of our line is positive. The acceleration is negative when the slope of velocity is negative. So that's 1 to 3 and 8 to 10. And then the slope is 0 from 3 to 6. That sort of matches with constant speed means 0 acceleration. So that was the same question asked a different way. When does it move at its greatest speed? All right, we kind of talked about this earlier. Speed is the absolute value of velocity. So speed means we don't care about positives or negatives. So it's going fastest at time equals, or when the velocity is 3, or speed is 3. Speed equals 3 at, this is a little bit weird of an answer, at time equals 1, at time equals 8, and from 3 to 6. So 2 instants where it's going 3 positive, and then a long span where it's going 3 negative. Graph the body's speed for 0 to 10. Well, speed is absolute value of velocity, so anything negative just becomes positive. So if I want to graph the speed, and I'll graph it in a different color, anything that's positive velocity, that velocity and speed are the same thing if you're positive. So that's the easy parts. But if my velocity is a negative 3, that means my speed is a positive 3. And I can kind of just connect the dots. So there's the speed. So speed doesn't have a sign. You remember that from physics. Speed doesn't have a direction to it. Speed is not a vector, if you want to use some more physics words. And graph the acceleration. Well, acceleration is just the slope of velocity. And we're running out of time, so we're not going to do that. All right. The good news is we're done with notes for the unit. So your job is to do only the 6 problems for worksheet 1. Obviously, that's a little misleading because I got lots of parts to them. Answers are posted in Schoology, so you can check and see how you're doing. Tomorrow or Thursday, block day, we'll go over some of these. You'll have time to work on the next worksheet. If you know it's going to be busy for you later in the week, you already know enough to do worksheet 2. There's nothing new coming before worksheet 2. It's just more practice. So you've got everything you need to be successful on Friday's test. Again, check your Schoology for answers.
I'm not going to be here for